So today I will be doing number 5 of the Faraday's homework, and the problem is as follows. A rectangular coil with n turns and total resistance R, length less than 1 and width less than 1 as shown in the figure, so this is the coil. The coil is moving into the uniform magnetic field B with constant velocity V, and it's asking for us to plot the induced current I2 as shown, and as a function of x when the coil is entering the region, and we have to clearly state the magnitude of the current. So the problem is essentially just saying that we are moving this rectangular coil with n turns into this magnetic field. So just to make things simpler, because we are just plotting the induced current as a function of x, I will label this point, this axis, x. And at this point, when the B field begins, will simply be 0 to 1. So let's just first find the flux, because it is needed to find the EMF. And the EMF is needed to find the induced current. So the flux, as always, is simply just going to be the integral from B dot dA. So plugging in what we have, we don't have to worry about B because it's uniform. All we have to worry about is our dA. So in this case, what will our dA be, or our typical element? Well, I'm just going to pick strips to make where I will call this length dx. So our dA will simply be dx multiplied with the width, or w. So that means if you plug it in, you will get flux is equal to the integral of b w dx. Simply plugged in our dA. And then we just have to figure out what our limits of integration will be. Well, since this equation is just going to give us the flux when this is moving towards this magnetic field, that means flux will only happen when it is inside this magnetic field. So, to make this even more clear, I have our rectangular loop as this blue square, and let's just say it's moving at the velocity v, as stated in the problem. So, as this is moving in, let's just say we wanted to find the flux at this moment. So how would we find the flux? Well, we could just use this integral, but what would our limits of integration be? Well, it will be from 0 up to this point right here, because the flux will only be where the loop is inside the B loop, the magnetic field B. So at this moment right here, we can call this point x. So only about half of this square is inside this loop right now. So it will be from 0 to x. So again, only the area of this rectangular coil that's inside the magnetic field will have flux, and the area will be from 0 to x. So, solving this integral, we will simply get bwx from 0 to x. That means flux will simply just be bwx. Now, finding the EMF, which will just be E is negative n d flux over dt, or the change of flux with respect to time. Well, n is given as just n turns, so we can just write that as negative n d, plugging in our flux, bwx over dt. Then, once we solve this, we're able to find the EMF. And as you remember, dx over dt is simply velocity. So, that means our EMF will simply just be equal to negative NBVW. Now, let's just find the magnitude of the current, or the induced current. Well, the induced current is simply equal to E epsilon over R, and we're taking the magnitude of it because that's what's asked of the problem, and we simply just plug in what we have for EMF, which will just be NBVW over R. The negative goes away after you take the magnitude. So now that we know the magnitude of our induced current, I'll just rewrite it. It's NBVW over R. We can simply now plot the induced current. Call this point 0. And let's just to make things easier, let's just say MBVW over R positive is simply going to be equal to clockwise, which means the induced current when it enters this magnetic field will be going this way, which means that the magnetic field will be coming out of the paper. And that means negative MBVW over R will be counterclockwise. So let's just call this axis x of t and call this our induced current I2. We'll label this as MBVW over R, and this will simply be the negative MBVW over R. So at 0, let's just say at this point 0 is the moment when the square loop, the rectangular coil, is starting to enter the magnetic field. So it's going to be at around right here when it starts entering the magnetic field. So at this moment, what will the induced current be? Well, since the flux is changing, we will indeed have an induced current. But the question is, would it be clockwise or counterclockwise? Well, since the flux is changing, and to keep the same flux momentarily, it will try to mitigate the change. So it will go, and we want a magnetic field that goes out of the paper. So what that means is it's going to be counterclockwise, or going this way, because due to the right-hand rule, it will show that a magnetic field is coming out. So the induced current will be going this way. So at 0, our induced current will be negative, but the question is up to when. So it will keep on moving and moving, and the induced current will stay the same as negative MBVW over R, because flux is changing. More and more area is starting to go in this B field. So as soon as it's fully submerged into this uniform magnetic field B, that's the moment when it won't have any more induced current, because flux will be constant. And at that moment, it will be at L. So at L, the induced current will be 0. Now, how long will it stay 0 for induced current? Well, it's going to keep on moving and moving until it starts leaving this magnetic field, which will be at 1. So at 1, when it begins leaving, that's the moment when another induced current will happen. And this time it will be clockwise, because in this case, it's losing flux. So to stop the change, it will induce a current that will go clockwise. because a clockwise current will give us a magnetic field that goes in the same direction as a uniform magnetic field B, because our B field is also going, the induced B field is going into the paper also. So at this moment, which is at 1, it will go to positive MBBW, or a clockwise induced current. And it will keep on going and going until this rectangular coil is fully out of the B field. And at that moment, the induced current will go back to 0. And in this case, the length will be at 1 plus L, because we know this length is L. So the moment that it's out of the B field, the induced current will be 0. So this will be the graph of the induced current. So just to reiterate everything I just said, what is happening at this moment right here is this rectangular loop is slowly entering this B field at a velocity v. And the moment that it enters, it will have an induced current that is going counterclockwise, just so that it will mitigate the change in flux. And this counterclockwise induced current, or negative MBBW over R, will keep on happening until it is fully submerged in the magnetic field. It is at this moment when there will be no more induced current, because flux will not be changing anymore. It will be constant. So it will stay, the induced current will be at 0 until it starts losing flux, which is when it starts leaving the magnetic field. And that point is at 1. So to mitigate the change, it will start inducing another current, which is going clockwise, or MBVW over R. So it will induce the current until it is fully out of the B field, and at that moment it is at 1 plus L, and that is when it will go back to 0. So the magnitude of induced current again is MBV W over R, and this is our plot of the induced current.